So today's talk will be given by Dr. Peter Dueben, the coordinator of machine learning and AI activities at the European Centre for Medium Range Weather Forecasts. He will talk about applying machine learning, and in particular deep learning, to improving the weather forecasts, and will also address the challenges in doing that. So Peter, please go ahead when you're ready.
Yes, thank you very much for the invitation to give this talk and the introduction. So I'm Peter, and before I go to machine learning, I will probably have to say a couple of words about this institute with a strange acronym, ECMWF, standing for European Centre for Medium Range Weather Forecast. You may not have heard about it, but it's actually close by. It's in Reading, so half an hour by train. And it's a research institute, but also a 24/7 operational weather service for medium range monthly and seasonal forecasts, which basically means that we're kind of focusing on global weather predictions and a couple of days into the future, but also kind of really looking into monthly and seasonal forecasts. We are an independent intergovernmental organization supported by 34 member states that you can see in this map on the right. And we have about like 350 members of staff, and we also have, to do our forecasts, we also have two rather big supercomputers, and we are the home of the so-called Integrated Forecast System, or IFS, which is basically known to be one of the best global weather forecast systems of the world. So basically, the reason for our institute really is that those member states came together and basically said, like, doing global weather prediction is quite a difficult task, so we should kind of join forces and actually kind of fund this international institute to kind of generate initial conditions and then also do global predictions for the medium range. Okay, this all for ECMWF, and now just this kind of one slide, which feels a bit silly to kind of present this to you because it is a seminar about machine learning, so you know basically all of this already. But what you see here is obviously a neural network, and the reason I show this slide is basically just to kind of lay the scene for the overall concept that we have in deep learning in particular, which is that we take inputs and we take outputs, and we basically learn the connectivity between the neurons to predict outputs from inputs, as we have done from a very, very large data set. And then once we've done this, we will be able to predict further outputs from unseen inputs in the first place. So the key here is really that we learn this tool as a black box. And this basically means that we don't really need a physical knowledge about the system as a starting point. And also, the key is also that as we have more and more data, we can actually increase the complexity of this network and make it more and better to actually represent this very complex systems that we're kind of training for. So what's new? Why is everyone now talking about deep learning and not necessarily 20 years ago? A couple of reasons. I only named two of them. First of all, the HPC, the high performance computing facilities have kind of basically exploded in their capability, which means that we can nowadays train much more complicated networks and can get to much better solutions in the end. And also the number of options how to kind of build those different networks has exploded. And we have something like 100 papers appearing every day in artificial intelligence at the moment. So we kind of really learn how to kind of build better and customized systems. I'm sure you know all of this, but basically what you should take from the slide is that in this talk, we basically talk about a system that is used to train, to kind of mimic a very, very complex nonlinear system without actually domain knowledge required to do so. And that's basically the essence of deep learning, at least from what I can say. And as the capabilities of those nets have kind of exploded as well, as you know, we now have also like an increasing number of application areas where we can use deep learning with very, very good success, for example, in image recognition, speech recognition, and so on and so forth. And basically what this talk is about now is a question how this looks for weather applications. So how, what does it actually mean that we have now this new tool, the new kid on the block in the capabilities of really represent very complex systems for weather predictions in particular. So weather and also climate predictions, why is it actually so difficult? I mean, if I would ask you whether you would trust a 5-day weather forecast, probably many of you would say, no, we don't. And this is not because we are lazy, but really because it's actually quite difficult to make a good weather predictions a couple of days into the future. Why is this so? Well, first of all, the Earth is quite big. So you see here a picture of the Earth taken from one of the Apollo missions, and you see that it's just huge, right? Which basically means that if you run a kind of computational fluid dynamic type system for it to represent atmosphere and ocean, for example, you will always have a lack of resolution. It will always kind of be limited by computational power for how fine scales you can actually represent in those models. And typically we're talking about something like a 10-kilometer resolution or grid spacing at least for an atmosphere model, for global weather forecast, or something like a 50-kilometer resolution for climate simulation. And this means that a lot of the processes that you will see in here, such as individual clouds, you will actually not be able to represent explicitly within your simulation. And that's obviously a big problem. And the other thing is that the Earth system shows chaotic behavior. So obviously atmosphere and ocean are fluids, so they will show nonlinear chaotic behavior as such, but also there are a lot of different components in here that you can see, like atmospheric chemistry, cloud physics, land surface schemes, sea ice, land ice, and so on and so forth, that are all interacting with each other in nonlinear fashions. And they would also show chaotic behavior in itself. So it's basically a very difficult nonlinear system and coupled to a huge number of different components. Also, it's true that some of the processes in these systems are not extremely well understood. So for most of them, we actually know the leading differential equations, but some of those processes we can actually, we don't know exactly the leading equations. And all of these things that I've just told you basically mean that we have a difficult problem here. I mean, we basically need to kind of really get good initial conditions and then run a forecast, but errors are going to kind of increase exponentially with time. And we have a lot of uncertainties here. Our models are huge. We typically have something like 1 million lines of code to kind of represent this complexity as well. And then it's always also very difficult to actually put these models efficiently on supercomputers. On the other hand, we have an enormous amount of data available. So just to give you an order of magnitude, we get all sorts of different observations into ECMWF every day. And we're on the order of millions, hundreds of millions of observations that we actually receive within 24 hours. So we really have a lot of data in principle about this very complex system. And not only observations, but we also have a lot of models that we're running every day that we could also potentially use for learning things. So a very complex nonlinear system with a lot of components and a lot of observations and model data. So this is ideal if you want for deep learning and machine learning, right? Basically, this sounds like a very good application area in principle. And therefore, basically, many application areas are there in this kind of framework of numerical weather forecasts for machine learning and deep learning in particular. One other thing that I want to point out is even if we would not be interested in the application of machine learning in numerical weather forecasts at the European Weather Center, for example, we would still need to look at it in terms to some extent, because also our hardware, the supercomputing hardware, is actually changing drastically at the moment towards the needs of machine learning, with in particular very low floating point precision and very high flop rates, so kind of a lot of computation at low precision. And we should also think about how to adjust to kind of this change in high performance computing hardware in the future, and to also for our conventional tools. Okay, so I've told you now that this is a great application for machine learning. So let's see what the limits are. So let's basically try to go all in and to generate a weather forecast system just based on machine learning. Just throw away all the conventional tools we have so far and just try to kind of learn a weather forecast from data. As I told you before, this idea may not be totally crazy because we have limitations in our existing models, and we also have this enormous amount of data. We have something like 210 petabytes of primary data lying around at ECMWF that is somehow related to the Earth system. So we made a simple test here. We retrieved data for a field called geopotential height at 500 hectopascal, which is basically just a two-dimensional field. And we have this available in a data set called reanalysis, which basically is the best picture of how the world looked like in the last couple of decades. It's so-called the Era 5 reanalysis. And we have this hourly. So we basically kind of get hourly data for these two-dimensional fields all over the globe for the last decades. And this sums up to something like more than 65,000 global data sets. And now we map this data onto a coarse resolution two-dimensional grid with 60 times 31 grid points. And now we just learn the equations using deep learning. So we just basically have a stencil of grid of points where we go through the grid, and we basically learn the update of the point in the middle of the stencil using deep learning. And we then stream the stencil through the grid and basically are able to update all the different points in the grid from 1 hour to the next. And once we've done this, we can basically make a prediction to the future. And this is really, doesn't require any physical understanding whatsoever. It's really just data, just the equations learned from data. So how does it perform? Actually, it performs quite well. So this is the field as it progresses, and one of those plots is showing you the reanalysis data, and one of those plots is showing you the neural network results. I'm not going to tell you which one is which, but you see basically the same features in both plots. I hope the video is coming out well, because if it's streamed, videos are always dangerous, but I hope you can see it all right. So basically, the neural network is picking out the dynamics very nicely. And also, if you draw forecast errors in this framework, you will actually see that if you kind of calculate a forecast error for a 5-day weather forecast, globally, you will get the black line here for the neural network prediction, and you will see the blue line for a very, very, very coarse resolution atmosphere model. And basically, what I take from the slide is, if I compare like with like in terms of complexity, I actually kind of get very similar results. And this is just me. I'm looking into the first ever deep learning applications 2 years ago that I looked into, playing around with something like this. So it's actually not too bad for this, right? It's still orders of magnitudes away from what you get with operational weather forecasts. So the magenta line is actually our operational score for the same quantity. But this setup only has less than 3,000 degrees of freedoms. So it's actually not too bad. So is this a future? Is this maybe what we're going to do in 10 years from now? And I would say it's unlikely, and there are a couple of reasons for this. First of all, the simulations are unstable. So if I just run it for longer, it's going to diverge at one point, because I haven't told it anything about conservation laws and kind of physical laws that are kind of really important for the system development in principle. It's also unknown in the setup how to increase complexity. So this is just for a 2-dimensional field. If I add fields to the system, I may not necessarily actually get better results. So it's kind of really difficult at the moment, because we don't really know how to make a high performance computing application out of something like this at the current stage. And also, even though I've told you that there is an enormous amount of data available in principle, we only have something like 40 years of satellite observation, which basically means that we only have something like 40 years actually of an independent time series. And if you think about global model forecasts, actually it's not this long a time series if you really want to learn all the details, in particular if there's maybe a changing climate. So there are reasons to kind of take this, that this may not be the best application for medium range weather forecasts. However, this is one of those fields that are exploding at the moment. So there are now a number of papers coming out, and people are improving the machine learning structures greatly and get much better results than I did here. So who knows? We will see in later on how far we get. And also, if you don't think about medium range weather predictions like 10 days into the future, for example, but really more like weather predictions like 1 or 2 or 5 hours into the future, which we typically call nowcasting, then it also may be a totally different story, because, for example, conservation laws, who cares for a 5-day weather prediction? And it's also not that you really want to kind of get feature interactions of very complex things in the atmosphere, right? It's more like advection and a bit less physics in the normal case of a longer simulation. And also, only local predictions are required, so you can actually kind of have a lot of independent training points if you want, if you have a global training data set. And there are very good applications. For example, this one is a video from a blog of Google that I can very much recommend, where they did a nowcasting application and really have results that are very convincing in comparison to the NOAA forecast, which was taken as a reference. So why is it so hard to beat conventional models, conventional forecast systems, if you want to do something like a 10-day weather forecast? And I think I think we at ECMWF, we should maybe be proud of ourselves, because actually our models are very good. So this is a high resolution forecast in the clouds. The cloud fields, one of the figures would show the cloud field over in, I think that's Indonesia, yes. From a satellite, and one of them is showing the cloud fields for a very, very high resolution simulation. And it's, even though domain scientists would not be able to tell you which one is which. So our models actually show an enormous degree of realism at the moment, and a breathtaking level of complexity. And they are running with billions of degrees of freedoms for like an everyday weather forecast, right? So it's not that we start from scratch. And also, we have basically decades of experience in building those models and also in process understanding. So it's actually kind of quite hard for a machine learning tool to kind of build the entire, and to beat the entire forecast system. And also, and this comes back to the complexity of the Earth system, if you kind of improve the model, you actually need to be very careful. So what's shown here is a so-called ensemble scorecard. So we basically made a change of the system here, going from double position to single position, which means basically reduce the number of bits that you use for forecast by a factor of 2, and still get hopefully good results. And this is kind of for so-called ensemble forecast. And we basically tested our system on forecasts of the past, spread over an entire year. And then we basically calculated the scores for the different quantities, and you see an enormous amount of quantities here. So you see different physical fields, and you see different height levels. You see all the different forecast days, 15 in total, and you see 3 different areas on the globe. You see the comparison against analysis, which basically means the initial conditions for the forecast. You see the comparison against observations, and you will see a lot of boxes here. Blue means that single position is better than double position, and red means that double position is better than single position. And you see that even though it looks more or less neutral, there's still a couple of boxes in dark red, which basically means that double position is significantly better than single position in these cases. And what I want to say is basically here, the system is very coupled. So even if you change something just over in the tropics, for example, in terms of cloud physics, you may get a response over the North Pole because the system is heavily coupled, and it may actually have a response that is kind of manifest itself in sea ice development or something like this. So kind of to add something significant to the system is quite difficult. And also, to kind of build this plot here, it actually requires more than 100 forecast simulations. So it's actually also a field which is very difficult to test whether things are better or worse. So using machine learning for weather predictions is useless then? No, obviously the answer is no, because otherwise I would probably stop talking here. Why is it not useless? Because basically, it's not just all about going all in or not. It's just also to kind of think about the different components of numerical weather predictions. So this is the workflow that we typically have, going from observations over data simulation. So that's the step where we basically merge observations with a forecast model to generate initial conditions. Then we're running a numerical weather forecast to kind of look into the future. And then the post-processing dissemination is basically post-processing the model output into something that is usable by the end user. And each of those steps is very important. And there are an enormous amount of different application areas of deep learning and machine learning in this workflow. So I've just kind of named a couple of them on the bottom half of the slide, and the color coding corresponds to the boxes above. And you will see basically that for each of those workflow components, there are a very large number of different application areas that we should explore. And we're really at the beginning still to explore the space. So we don't quite know yet which of those cases are going to work out well, where machine learning is going to be better than conventional tools, and which of those cases are probably not going to be so good. So there's a big question in the room now. So what will machine learning actually kind of look like in 10 years from now, from the perspective of numerical weather predictions? And there's a scale here. And this scale goes from something like machine learning will not have any long-term effect at all on the left side, and machine learning will replace conventional models whatsoever on the right side. And the scale is kind of from dark to white and then gray in the middle. So there are a lot of application areas where it's kind of quite clear that it will work out quite well. And there are other application areas, for example, the learning of the equations, where it's not so clear whether this is actually going to work out well. And if you ask around in the domain, you get very different answers where we're going to be on this scale in 10 years from now. So some of the very senior, very prestigious scientists would tell you we're going to be on the far left and there's just a wave going through. And others will actually tell you we're on the very far right and we should kind of rethink about the entire way how we make weather predictions in the future. And I would say the uncertainty range in this kind of scale is still very, very large at this point. And we really need to kind of explore the space in the next couple of years and to understand how it will actually narrow down. I'm sure it's going to be more on the right than on the left side, but we will see. So the state of play is really that there are a lot of interesting application areas for machine learning in weather and climate predictions. We are only at the beginning to explore the space. And what I'm going to do in the rest of the talk is basically I'm going to talk you through a couple of example applications for machine learning at the European Weather Center. And then in the end, I will talk about the challenges that we are facing and that we probably should be addressing in the near future. So I'm going to go through this workflow. I've kind of have put it again on the upper right here. So I'm going to go through the workflow with the applications. So we're going to start with observations on the left side. And this is an example of an application for machine learning to detect wildfires, or the probability, actually the risk of wildfires, based on observations, but also model forecasts. And that's work done by Ruth, Francesca, and Claudia at ECMWF. And they've basically picked 15 variables that are somehow related to wildfires. And then they looked into a satellite product, the so-called global fire simulation system. And then they identified basically for which points they have seen wildfires based on the different inputs. And once you've done this, and once you've set up like a 12,000 data point data set, you can basically learn the probability of wildfires using decision trees. And once you've done this, you can basically predict where there's very high likelihood for wildfires. And the best accuracy that they obtained was something like 77%, which doesn't seem too great, but actually it's very important, right? I mean, it's if you can predict the ignition of wildfires with a probability of 77%, that's quite good. And also the ignorance matrix on the left shows you, if you plot true labels against predicted labels, most of the cases are actually on the diagonal, which means that you do something useful with your prediction. Okay, the next one is data assimilation. So what we do here is, as I said before, we basically get observations in, and then we blend these observations with a forecast model to generate initial conditions. And this requires to actually make an estimate for both the errors that you have in observations and also the errors that you get in forecasts within the forecast model. Typically, we don't estimate the error of the forecast model, but only provide an estimate for the errors of observations. However, we now kind of do the second step in the so-called reconstraint for var, which is a specific tool we're working with, and also try to predict the error that we get within the forecast model. And the results can be seen on the figure here. So what this is a pressure. It's a kind of cross-section of the atmosphere at a certain pressure level, and on the x-axis you see time, so it's evolving over a couple of months. And Patrick and Massimo, the two guys working on this, basically learned the model error within the data simulation framework by always comparing the model trajectory with observations that they could trust, so-called GPS RO temperature observations. And you will see that the color is changing from left to right, which basically means that they successfully learned the forecast error within the data simulation framework. So that's great news. At the moment, this is still a very simplistic, if you want, machine learning tool in a very complex data simulation framework, but we're also now going to do the step to actually kind of go to deep learning and also kind of try to really predict the error of the forecast model using deep learning, also in a collaboration with NVIDIA. So the next step is now the numerical forecast model, and I have a couple of examples here. One of them is that you can actually, even if you don't believe in learning the equations for the atmosphere, you can maybe still learn the equations, for example, for an ocean model. Why is there any difference? Basically, because if you make a 10-day weather forecast, for example, the atmosphere is really, really important, obviously. The ocean is not going to change too much in a 10-day weather forecast. It's not unimportant, so it's definitely better to have an ocean than to have no ocean. But maybe it doesn't really make sense to kind of run a full 3-dimensional ocean model, but maybe you can basically try to get the same dynamics right with a low-dimensional ocean model. And I'm not saying that ECMWF is going to this direction. It's just something that I'm personally interested in, and I'm doing some research here. So the motivation is clear. We want to have a low-dimensional ocean model for medium-range weather forecasts. And the testbed is now a 3-dimension, a 3-layer double quasi-geostrophic model. That's quite a mouthful. Basically, that's an idealized case of an ocean model, which is working in a rectangular domain with only 3 levels in the vertical. It's kind of much simpler, obviously, than a real ocean. We have data for 40 years, a time series. And what we do now to get to low dimensions is that we do a principal components on this very long time series in 3-dimensional space. And we only keep the 8 most important principal components for this study. So now we have 8 component time series over a very long time. And now we don't know how to kind of make a dynamic model out of this, but why not just learning it with deep learning? So we can actually learn the equations for those principal components. So we use neural networks to learn the equations of motion. We're basically working with very standard machine learning structures like LSTMs, 2 hidden layers, 50 neurons, blah, blah, blah. And this is also still within the optimization phase, I would say. But results don't look too bad. So if you look at, this is kind of our two-dimensional domain on the top, and we are interested in the frequency spectrum here. And basically on the left, you see the true frequency over 10,000 days. And on the right side, you see the frequency that we get with our 8 degrees of freedoms model. And you see that it's covering the frequency actually quite nicely, given that you only have 8 degrees of freedoms. And that's work done by Niral Agarwal from Imperial College and also Pavel Berlov and a couple of others. And I'm looking forward to kind of get more work done here. It's fair to say, though, that it turns out that actually if you kind of take more of the conventional learning approach, where you use linear regressions to kind of propagate those principal components and add red noise stochastic forcing in a very smart way, you actually get even better results at the moment. So it's still, maybe deep learning is not the best way to do it, but in principle, learning methods seem to be kind of very promising. So still with the forecast model, what we do now is that we emulate the so-called radiation scheme with deep learning. So what we do is we run our forecast model, and then we store input and output pairs of one of the components of the model, which is the so-called radiation parameterization scheme. What this is doing is basically it's kind of getting the impact of the radiation coming from the sun and the interactions with the clouds, and also thermal radiation from the ground going upwards and the interactions with the clouds, and basically it identifies how much energy from this radiation is kind of dumped at the specific levels of the vertical in the atmosphere. And it's obviously quite important for the energy transport. And we basically have now input output pairs for a long simulation, and we use this data now to train a neural network to basically do the same thing that the radiation scheme did in the first place. And once we've trained a neural network, we can replace the radiation scheme by the neural network within forecast simulations. Why would you do this? Basically, the only reason to do this is because it's very likely that the neural networks are going to be much more efficient than the conventional scheme in terms of high performance computing. So basically, it's very, very likely that the deep learning tool will be much, much faster on a supercomputer than the original scheme. And also it will be more portable. So to kind of port something like the radiation scheme onto, for example, GPUs is difficult. To port a neural network to GPUs is trivial because we have all those amazing libraries that we can work with. So this is a collaboration now between us at ECMWF and NVIDIA, and we get quite good results again in terms of the realism of the radiation as it looks like. So this is a two-dimensional plot, and you see the surface downward solar radiation given from the original scheme and one from the neural network, and you will see that the fields look very similar, and I again will not tell you which one is which. And we also get quite good speedups. I mean, it's very difficult to actually kind of quantify those speedups because we're talking about a CPU optimized version for the conventional radiation scheme and a GPU optimized version for the deep learning tool. But we are confident that we will get something like a factor of 10 in terms of computational cost as we switch to the neural network for the specific scheme. However, it's fair to say that the results are not neutral yet. So we still get a degradation of results as we kind of go from the conventional scheme to the neural network, and more work is required here. And also, it's fair to say that this is a very active area of research, that there are a number of papers coming out that really do the same thing, and there's more to come just simply because more people are going to look into this. We also have a very good collaboration with Matthew Chantry and Tim Palmer here in Oxford to kind of do the same step for a different part of the model, which is the gravity wave track scheme. And basically, we have two different parts here, the non-orographic and the orographic wave track. Basically, this is the interaction of kind of flow over mountains or kind of rough surfaces, and they are basically spawning waves that are kind of propagating up in the atmosphere and can be very important as well for the energy transport. And this is also something that we cannot resolve properly, and therefore we need to these kind of specific schemes for that. And again, we get very good results if you compare the original scheme with the neural network. So the difference is very small, and we're kind of confident that the results will be very good if you kind of go back to forecast simulations. It's also a nice relationship that Matthew gets here. So basically, this plot on the right is now showing you the mean squared error that you get for the parameterization scheme plotted against the complexity of your neural network structure that you have. So you have floating point operations on the x-axis and the error on the y-axis in a log-log plot. And the dots are basically kind of the results you get for different solutions for the neural network. And you see that it's like a straight line in the log-log plot, so something like a power law behavior in terms of complexity of the neural network and the accuracy of the prediction that you have. However, so that's the good thing. The bad thing here is that basically if you kind of now make the cross for the original scheme, you get this cross being slightly below the neural network cross, which basically means that actually the original scheme has lower complexity than the deep learning solution for the same accuracy level. That's not too much a reason of a concern, because the number of floating point operations is not a very good quantity to look into in terms of performance, but still it tells you something that you not always deep learning is going to be beneficial in terms of cost. And also, it's fair to say that we get good results for the non-orographic part of the gravity wave tracks, but we don't get so good results for the orographic part of the gravity wave track, simply because the orographic part is very much local where topography is, and therefore it's kind of very much undersampled in the data set, and we haven't really found a very good trick to kind of really get good results in the data set where you often have nothing happening, and then in very few cases a lot is happening. Okay, the next one for the forecast model, this is again work here in a collaboration with us and people here in Oxford, Jan Ackman and Tim Palmer in particular. And what we do here is that we basically try to precondition a linear solver using deep learning. Linear solvers are very important for semi-implicit time-stepping schemes that are often used in atmosphere and ocean models. And if you use the linear solver and the semi-implicit time-stepping scheme, you're going to be able to work with longer time steps than explicit schemes, but the solvers are going to be very expensive. The efficiency of the solvers then depends crucially on the preconditioning that you're using. And the preconditioner of the solver is basically doing nothing else than approximating the inverse of a very large matrix. And we now try to do this approximation of the inverse of a very large matrix using deep learning. So the test bed here is a global shallow water model at 5-degree resolution and with real-world topography. So it's like a two-dimensional atmosphere model if you want. It's obviously far away from the complexity of a real-world model, but it's not too unrealistic in terms of the two-dimensional motion on the sphere, on the Earth. And the method is we're using a neural network to train, to learn the model state of the next time step, which is basically the same as kind of predicting this inverse of the large matrix. And the results look quite good. So this is now a solver step for the solver step that is happening for from one time step to the next. And basically, you have the residual of the solver and the number of iterations. So as the solver is iterating, the residual goes down and the accuracy of the solution is getting better and better. And at one point, you reach this horizontal line, which basically says that we consider it to be good enough and we can stop the solver. And without a preconditioner, we're using something like 12 iterations for the solver. With our machine learning preconditioner, we're only using 7. So we actually reduce this number of iterations quite significantly. The implicit Richardson preconditioner, which is used normally, would get down the number to 4. So it would be more efficient if you want in terms of the number of iterations. However, it's also more complex in terms of the computational resources required. So actually, if you compare again like with like in terms of number of operations, the machine learning preconditioner is actually on par with the implicit Richardson preconditioner. So it turns out that this approach is working and it's actually quite cheap. And also the results that we found to be interpretable, because the machine learning, the deep learning structure that we kind of worked with in the end was very simplistic with only one layer, and you could actually understand what the machine learning tool was doing here. And also the big pro is that it's easy to implement. So you wouldn't need to precondition in the first place. You would kind of just take a linear solver, run it for a long time, and then without precondition, and then you can just learn how to precondition with deep learning. So that's really interesting. Now I'm going to the last box, to post-processing and dissemination. So what we've done here is, it's now a collaboration with Thorsten Höfler and his group at ETH, is that we looked into so-called ensemble predictions. So at ECMWF, we often perform ensemble predictions that do not only perform a single weather prediction into the future, but we actually kind of perform a number of forecast simulations into the future. Normally we do 50. And why would you do this? Basically, because it's not only interesting to know the temperature in 2 days from now, but it's also very important to know the probability distribution of the temperature in 2 days from now. For example, whether it's going to be above 25 degrees or something like this, because then you may need to take another action than just knowing that it's most likely going to be 20 degrees. So we have this ensemble system and it's working very well, but it's also very expensive because you need so many ensemble trajectories. So the question is whether we can use deep learning to actually kind of boost the skill of an ensemble with a smaller amount of ensemble members, and kind of just introduce a nonlinear mapping to kind of get the skill as if it would be with an ensemble of a larger number of ensemble members. So we have now an ensemble with 10 members that is available for the last 20 years, and we now try to kind of get to the same skill with using only 5 members of the ensemble plus a neural network correction of the results for 2-day weather forecasts, both for temperature at 850 hectopascal and geopotential height again at 500 hectopascal. And the results you see, I think this is for temperature on the right side. So you see the CRPS is a continuous rank probability score, which is basically the skill score of our ensemble forecast, and basically lower means better. The red boxes here are the results you get from an ensemble with 5 members and 10 members for different forecasts. And you see that clearly the 10-member ensemble has a higher skill than the 5-member ensemble because the bar is lower. And now our deep learning solutions are in blue, better than the 5-member ensembles without post-processing, so that's good news already. But if we even if you train the neural network to actually improve this one skill here, the continuous rank probability score, we actually get even better results when comparison to the 10-member ensemble here, because we do not only kind of improve the spread and the skill, but we also make a bias correction of the error. So actually, this is really promising, and we should look into more details how this can be kind of done with more complex input fields, and for really be useful for operational schemes. Okay, and also I want to say that even if you don't use very complicated 2-dimensional and 3-dimensional deep learning structures that require a lot of high performance computing, you can also do a lot with just using, for example, decision trees. So this is a tool developed mainly by Tim Houston at ECMWF, where he's using decision trees to actually compare the ensemble forecasts to observations that have been done within the grid points and the grid cells, and he's using this tool to improve the probability of rainfall, the prediction for probability of rainfall, and he's getting quite good results in terms of that you actually get an earlier signal and a more consistent signal with higher probabilities if you're using this post-processing tool. I'm not going to go into too much detail here, but basically this is already used in operational forecast with us. So this was kind of a run through a number of different application areas, and I hope that I convinced you that it's actually useful to look into the application of deep learning and what we can do with it in numerical weather forecasts. Now I'm coming to the challenges that we're facing. And I mean, basically, we're now using a black box, as I said a number of times before. There's no fundamental reason not to use a black box within weather and climate models, but there are unanswered questions at the moment that we need to think about. And I should also phrase, I mean, it's not the first time that we're using machine learning as such, right? I mean, if you think about principal component analysis or all sorts of other things, regression techniques and parameter estimations and so on and so forth, machine learning is all over the place, but now it's just kind of the use of deep learning, which is kind of really new, the new kid on the block. So there are a lot of questions here. For example, how can we actually use the knowledge about the Earth system to improve the machine learning tools? So how can we kind of, for example, project the knowledge about differential equations into the architecture of the deep learning solutions that we're working with? How can we diagnose physical knowledge from the machine learning tools? Not only because it would be nice, but also because it would be important to build trust. So if you have a tool that you kind of learn, for example, to kind of learn how clouds are interacting with the rest of the atmosphere, it would be very important actually to also understand what the tool is doing, because otherwise you will be very likely generating a tool which is good for 9 out of 10 features, but one feature may be represented incorrectly. And also it would be required to kind of build trust with the domain scientists who are normally very skeptical. Also, can we improve errors for neural networks and secure conservation laws? So can we kind of make tools that are actually also conserving energy, for example, or momentum, because this is going to be important for, in particular, for long-term simulations. And again, it's about trust as well with the domain scientists. Can we guarantee reproducibility? So if you train the same tool basically on a different data set that's slightly different, do you get the same results? Because if not, this is going to be very dangerous for operational weather predictions, because you always would need to be able to kind of bring back your forecast scores into the same level if you make a small change to the system. How can we find the optimal hyperparameters for deep learning? I mean, that's probably a technical question. I'm sure we will make more progress in this one as we kind of learn more about how to use deep learning. But still, at the moment, it's a very open space, and people need to make a lot of tests and spend a lot of computing time to actually kind of explore this hyperparameter space for deep learning. Can we effectively scale machine learning tools to high-performance computing applications? There, we also need to kind of do much more in terms of how to actually, once you have, for example, a bias correction or a correction of the post-processing, how can you kind of really make this run efficiently on your supercomputer that you have? In particular, because most of the computers that I've worked with for weather and climate predictions nowadays are CPU-based. So it's also not exactly the same hardware. Can we interface machine learning tools with conventional tools? And this is also more complex than you may think. You think it is easy, but actually kind of to build Fortran, and we have Fortran tools normally, and then we're now putting in a Python library to kind of work with GPUs, and this is more complex than you may think. Can we design good training data? In particular, if you're kind of interested in kind of time stepping of a model, you need very short time steps, and typically the data that we have on the archive is kind of with very large time steps like hourly data, which is often not usable. So again, we need to think about how to improve this. Can we explore the full phase space? If you have a climate change, your weather patterns are going to change. So if you train a machine learning tool from current weather, it may not be working in the future. So things like this, again, to build trust, we need to understand how to explore the full phase space for our solutions. I'm not saying that these problems here are not touchable. So definitely there's an enormous amount of people working in looking into exactly those questions here. And I'm sure a number of those problems will just vanish in a couple of years. But it's still, these are very interesting research questions at the moment. And I can only urge you to look into them and help us to kind of tackle these challenges. For an operational weather forecast center as ECMWF, you also have specific challenges. For example, we have a lot of data lying around in our archive, and now we face different patterns of user requests and people asking for more and more data, which is just an infrastructure problem, but it needs to be addressed. We also will need to keep up with the development of supercomputing hardware, and have 2 slides more to come on this one. And also we will need to kind of learn how to support the community to actually make the best out of machine learning in the next couple of years. So we're building out up our own cloud structure at ECMWF at the moment, the European Weather Cloud, and I'm sure that this is going to be very handy in the future. And also we have a workshop on machine learning in October that I can also invite you to. Hopefully it's not going to be virtual, but we'll see. And also we have a machine learning seminar series at ECMWF now. And again, I would welcome you to kind of participate in those talks as well. So my personal vision on the way forwards, if you kind of have weather and climate models in the middle and the machine learning part on the outside, I think we should try to link the 2 domains really with a top-down and a bottom-up approach at the same time. Bottom-up, because I think we should look into idealized equations and really try to understand how to, for example, build deep learning solutions that are conserving energy, momentum, and so on and so forth. Also bottom-up, because we should learn how to kind of use machine learning for uncertainty quantification in particular, because there's a lot to gain here to really understand what the biases of our conventional tools are, and what how to represent variability of subgrid scale noise, for example, into our systems. Top down, because we should really think about building scalable solutions that can train from terabytes, if not petabytes of data in the future, to kind of make the best out of our weather forecast model at the moment and the different application areas that you've just seen. And also, I think we should think about benchmark problems. That's also top down, where really the community come up with something, with specific problems that are really important for us in terms of deep learning. And then we let the machine learning community to really kind of consider those benchmark problems. And one, like an ImageNet type of problem, basically for weather and climate applications. And we've done the first step by having the first benchmark problem published in a paper. So the focus should be on useful tools here, because if we can't show that those tools, if we can only develop very nice tools, but we can't show that they're actually going to improve our predictions in 2 years from now, for example, a lot of the effect of machine learning is going to be gone by then. And also, I'm pretty sure that this will require machine learning solutions that are very customized for weather and climate predictions in particular. So at the moment, we're often using very standard networks, like networks trained for ImageNet, and then apply them to the atmosphere, and just thinking that it's like a picture, but it's obviously not. So we should also really think about customized application. Okay, the last topic I want to scratch here is the question whether we can actually use deep learning hardware for our conventional models. So I told you before that we have a big supercomputer, and I also told you before that machine learning has a very strong impact on how hardware is changed at the moment. So there are a lot of machine learning accelerators that are really focusing on low numerical precision, 16 bits instead of 64, and very high flop rates. And we will need to learn how to make use of this hardware if we want to make the best use of future supercomputers. Just one example, the Tensor Core of NVIDIA is basically the hardware accelerator for machine learning applications on NVIDIA's Volta GPUs, and it's optimized for half precision matrix multiplication because that's exactly what you need for deep learning. And it provides single precision output. And if you use this Volta GPUs and the Tensor Core, you get a flop rate of something like 125 teraflops instead of 7.8 teraflops for double precision on the same hardware. And as a matter of fact, if you use those Volta GPUs, you actually can already today work in exascale and sustained exascale supercomputing. So there's really a lot to gain if we could port some of our model tools to this Volta GPUs or other machine learning hardware. So can we use Tensor Cores within our models? And we've done a study here looking into the most expensive kernel of our model simulations. So if you kind of look into the cost distribution of a very, very high resolution simulation in a specific mode here, non-hydrostatic mode, you will see that more of 50% of the cost that we have is spent in the so-called transforms. And the cost for the transforms is dominated by the so-called Legendre transformation, which is basically nothing else than just a large number of standard matrix multiplications. So exactly the piece of dense linear algebra where the Tensor Cores are optimized for. This ratio is not always 50%. For some configuration, it's lower, but it's definitely the most expensive kernel that we have in our models. So if we could rescale the inputs and output fields, it actually turns out that you can use half precision for this kernel. So we've done a test, and basically we found out with some kind of smart readjustment of the input and output fields, we could actually go to half precision. And then if you think about the forecast error, we could also have quite good results by using half precision or the special feature of integrating in half precision, but providing a single precision output. And we've published this in a paper led by Sam Hatfield, who was also at the time still a PhD student in Oxford, and Tim Palmer, who's also kind of, and Matthew Chandler, who's also in Oxford. So a lot of Oxford here. And we basically show that you can use potentially this hardware for the Legendre transformation. However, there's a caveat. This was all done with an emulator, so we haven't really ported it to the hardware, which means that I can't give you the exact number for the speed up that we get. And obviously the peak performance numbers are maybe kind of a bit misleading. So it's not that we expect a factor of 16 here. But there's more to come. I think this is very, very interesting research. Okay, these are the conclusions. I don't think I should read them out loud. And I will leave you here with this. I want to thank you for your attention. And here's my email and Twitter. So if you want to reach me, you're very welcome to. And I would be very happy to be in contact. Thank you.
Thank you very much, Peter, for this wonderful talk. So we'll open the floor for questions now. And maybe just a comment from my side to give people some time to unmute themselves. So this approach with having challenges and benchmarks has really worked well for the particle physics community. We've had 2 of these challenges, and it's worked well for us. So I think it's a very good way forward.
Thanks. It would be great if you could point me to those. Actually,
sure.
It would be very interesting. Yeah, I strongly believe in this because. I mean, basically, what we need to achieve is to make domain scientists, in terms of machine learning, to be able to kind of pick their brains on our problems without then needing to understand what they're actually doing with, right? I mean, we basically need to formulate those problems in a way that they can download terabytes of data and kind of make magic, and then come back to us and show us how to do it really.
Yeah. So questions? From the audience? So there's no need to be shy. Yeah.
So this is Louis Lyons. Could I just ask, you were explaining how in predicting the weather, the temperature next week, you were using not just one prediction, but 5 or 10 or more. And then you were using deep learning in some way to do even better with the finite number of predictions you have. Could you explain a little bit more how that's done?
Yeah, of course. So I think the concept of ensemble simulations really is just think about a tropical cyclone approaching the US coastline, for example. And you do not only want to know where the tropical cyclone is going to hit the coast, right? You want to know with what probability, for example, it's going to hit a big city like Boston or whatever. So therefore, ensemble simulations are actually quite good because you can make 50 ensembles members, and you have 50 trajectories of the tropical cyclone, and then you can basically kind of have an estimate of the probability distribution in the end. And that's what we do all over the place, and it's actually kind of worthwhile for a lot of different application areas for weather predictions. In particular, if you look into a couple of days into the future where uncertainties are rather large. So what's happening now is that we basically, we're probing this PDF using ensemble members. So you have kind of just 50 samples, and now we kind of get a probability distribution that is probing the real probability distribution as you would have if you would have 1 million members, basically. And deep learning comes in now in two different ways. First of all, deep learning can do a local bias correction. So it can actually kind of reduce mean biases that it learned from the past by comparing past predictions against how the weather then looked like in the end. And also it can change the way we kind of think about this probability distribution. So it can actually correct for problems in the probability distributions, both in terms of the ensemble may actually kind of be over dispersive or under dispersive. So it's kind of also a trick of tuning the ensemble to actually have the right probability distributions, but also in terms of the nonlinear part that it may not be perfectly Gaussian, for example. I hope this makes sense.
And there's a raised hand from Tim. Please go ahead.
Hi, I was going to make a comment, but if I don't want to hog the floor here, but people may not know, but one of the things that's quite commonplace at the moment is for, you see, the European Centre that Peter talked about is as it says, kind of an amalgam of 30-odd countries. Quite often at the moment, what happens is the forecasts go out to the national meteorological services, and they run what are called limited area models. So they have their own kind of in-house, very, very high resolution model, you know, which might go to a 1 kilometer grid or something like that, but over a very limited domain. And these are, you know, the rationale behind this is to produce a higher resolution model that you know, may give more detail to the forecast over, you know, regions of high topography and so on. Now, the ability of deep learning to do this kind of downscaling, I think, has enormous ramifications if it turns out to be successful, because it completely undermines the need for this separate you know, limited area model type of forecast at the regional Met services. So this is a potential application, I think, of machine learning, which could actually quite transform the way in which global meteorology is done, in this kind of way of going from the global models to the downscale models. So I think this will be an extremely interesting area to see how it develops.
Let's see. There was Tim. You have Tim's talk, Tim's name on a couple of slides. So we have a very good collaboration with Tim in Oxford. And I can only, if you're interested in machine learning application for weather and climate, he would be a very good person to talk to, I guess.
Okay, there's a raised hand from Ankur. Please go ahead.
Yeah, thanks for the talk. So recent research has shown that that climate change can be detected on even daily timescales by its affecting the spatial global distribution of temperature. Since machine learning is not as effective at extrapolating to unseen scenarios or scenarios that have a fundamentally different distribution than the training data, for me that problem with machine learning reconciles with climate change scenarios?
That is a good question, and that is obviously a matter of concern, no question. I mean, deep learning tools can only interpolate it. They can't extrapolate, and they're known to kind of fail actually if you extrapolate them beyond the training skill, right? So we need to be careful there. There's no question. I think it's going to be very different. It depends on where you apply it to, right? For example, if you're talking about the radiation scheme emulation, for example, you have billions of samples and they're very local. So you can actually sample a lot in this parameter space if, for example, suddenly the UK would turn into the UK weather would turn into weather like in France or something like this, you would still have learned for the specific weather, basically, because you've previously learned for France. So there are applications that are more resilient here, but yes, you're right. You need to be careful. You could, in principle, also run climate models. So if you learn from models in the first place, you can run climate models. You can run them into higher temperatures, and then you can also explore this space. But you need to be careful, and also you need to. I'm sure we will also find more research in this area. For example, for the radiation, we're now trying to kind of understand the data that comes into the model, to the neural network that we try to learn, and then also try to extrapolate within the data set where we're training from. I don't know whether this is going to work out or not, but you can think about those approaches. All recommendations are welcome.
Yeah. I think that that level of attention and care is pretty important, especially, do you think that affects how you create a train set and a test set? So, because a lot of the more recent years and the future years will be different from the previous ones, how do you think about dividing the data in those two ways?
It depends very much on the application, right? I mean, basically, often you have actually climate model simulations where you can generate data from the future, at least in an approximated way. But it's something to look into, and I'm sure that's one of the areas where we want to make progress in the next couple of years, to actually understand how to, for example, also extrapolate neural network solutions, or to at least make sure that then not suddenly everything is blowing up when the Arctic becomes ice-free or something like this.
Thanks.